So, hi guys, this is Dr. Edwards again. I'm going to give you here a quick video on two important concepts in quantum mechanics. The first will be superposition of stationary states. And I'm taking that from Quantum Mechanics Demystified book, one of the books that we use. And the other will be some fundamental concepts on vector/matrix algebra. And I'll take that from David Griffith's book. And then I'm going to give you some homework problems on these two concepts, okay? So let me get started then quickly here. The whole idea then, expansions of wave functions and finding the coefficients. What does it mean by this? So we've already done the infinite square well, and we've gotten then the stationary states for the infinite square well. And so that will be the backdrop of this discussion. Suppose now that we talk about not only the system being, and system is one particle, being in state psi 1, or psi 2, or psi 3, or psi n, but later will be in some combination, some addition of those states, any two of them, or any 5 of them, or any 100 of them, etc., etc. The idea is this important phrase in quantum mechanics. Of course, it's been taken from classical mechanics, but it has a slightly different additional meaning in quantum that it doesn't have in classical. Superposition, superposition. So what we're going to argue here is that these sister functions, psi, and here we're calling them phi sub n, and the time aspect of the state is in the exponential, and that's going to be set to the side. And it can always be set to the side for potential energies that's not a function of time. And the infinite square well, the potential energy is not a function of time. So that's what we're going to use. Okay, so let's go on with this now. Okay, first we want to talk about states collapse. What does it mean? Although you may have a superposition of states in this manner, where psi is written as some n going from 1 to infinity of c sub n phi of n of x e to the negative I omega nt. Then suppose you were to measure psi, measure this state. What are the possible results of the energy? The energy is going to be one of those particular unique quantum energies that you can get. The system can't be in any sum of these energies. It's going to be in one or the other. And right after the measurement, the system is going to be in the corresponding phi state. If you measure this psi, it will hit on one of these particular energies, EI, and the system ends up in this phi state. We call that state collapse. It can't be any strangeness about this. It's in one of these specific energy states that it can be in, or one of these specific quantum states. Although before the measurement, the system is in some combination of them. As soon as the measurement is made, the system falls in one or the other. Okay, let me go on. Another important feature that we're going to have is this inner product of function has an analogous way to inner products of vectors. Ergo, while I'm talking about these in the same. These sister functions have this relationship with each other. So this is the definition of the general definition of inner products of two functions phi and psi. It is the integral then, and it's going to be a definite integral, but we don't put the limits here now, of phi star, the complex conjugate of phi, times psi. You get the integrand specifically, and then you can integrate it. We call this the inner product. Okay. Now something interesting occurs. For these set of stationary states, it turns out that the integral of any one of them with itself is 1, and the integral of any one of them with one of the sister function is always 0. Or you can represent it generally with this Dirac delta function. Let me go on. So then finding this coupling coefficient, let me go back to that so you can see it here, C sub n. So C sub n figures to be very important in this context as well. Why is this so important? Because as I said, if the system starts out in the psi state, and then as soon as you take the measurement, it then becomes the probability of the system is in this psi sub n state is the magnitude of C sub n squared. And C sub n, the magnitude is always going to be between 0 and 1. If the system is exactly in one of the quantum states, then C sub n is 1. But if it's in some combination of them, then C sub n will be some sum aspect, as you will see here. The sum of the C sub n's have to add to 1. Let me then teach this example. A particle of mass m is trapped in this one-dimensional box, as we talk about, the infinite square well, of width a. And this is now the sum of the states, sum of 3 of the stationary states. N equals 1 here, n equals 3 here, n equals 4 there. Now, so ostensibly, it should be a sum of these stationary states, which are the square root of 2a sine of whatever it is, 2a sine of whatever it should be, the square root of 2a sine of whatever. All these are normalized except for this one. So you have to handle the process to get the square root of 2 over a for this one, just as it is for that one. When you do that, you will see that the normalized states then are in this manner. Therefore, for n equals 1, the stationary states is the square root of 2 over a sine of n pi over a, and the energy is this quantity. For n equals 2, it is this quantity here, the square root of 2 over a sine of 2 pi x over a, and the energy is that, as we've already said. When n equals 3, it's that, n equals 4 is that, etc. So you go on here. Now, having made the adjustment, right here is where the adjustment is made. And you see now that these are all normalized states right here. And these are coefficients. You see here that C sub 1 is I over 2. C sub 3 is 1 over the square root of 2. And C sub 4 is a negative 1/2. All of the other C sub n's are 0. Therefore then, what are the probabilities? So what you end up with is this quantity right here. That is the normalized wave function of psi. If you integrate psi with itself, you had better get 1 here. Okay. So therefore then you can see the coefficients spelled out here as they should be. All of the other coefficients, those that are not shown here, are 0. Okay, so what does it mean then? So since C sub n is not present, blah, 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 fine. So E sub 1, suppose the system then, we investigate what is the likelihood that the system, if you measure it, is going to have energy E sub 1 or be in the phi sub 1 state. That then becomes psi star 1 times psi star. And C sub n star, C sub 1 star is a negative I over 2, and C sub 1 is a positive I over 2, so that's 0.025. That's 25% chance that the system is going to be in the E1 energy in the phi 1 state. What is E sub 3? And the probability PE of 3 is 1/2, 50% chance that if you make the measurement, it's going to be in that state. And the last one here is E sub 4, is 1/4. Notice that the sum of these had better add to 1, which it does. That's what I wanted to share with you about this, okay? Let me go to the next portion here and take it from here. So this now is going to be a quick introduction on vectors and matrices. The whole aspects of linear algebra become extremely important in quantum mechanics. And here, what you may have not seen before is the direct notation of representing vectors in Hilbert space. So I, and K are in Euclidean space, but now we're going to create this other structure, this greater than symbol and the vertical line, just a syntax, just something that humans create so we can keep track of what we're talking about. Then the whole idea of adding vectors, just as you could add vectors I, J, and K and get another vector, you do the same with these kinds as well. Okay, and the vectors rules are commutative. You can commute two vectors. Doesn't matter if you add B to A or add A to B. So here we're adding vector alpha to vector beta, or add vector beta to vector alpha. So this whole idea, so I want you to go through and read all this portion. I'm going to have it for you to be able to read as well. So I'm going through it very quickly here, but I'll have it available. We will go on here. So the whole idea of unit vectors as well in this Hilbert space, where we can talk about this whole set of unit vectors. Whereas real space, I, J, and K is just 3-dimension. You can have an n-dimension of mathematical structure in these quantum states, okay? And so let me go on to the matrix portion here. So you can talk about inner products as well. And I'll mention the Schwarz inequality as we pass through it here. And you go through it and read this portion here. Okay, the Schwarz inequality is there. So now we come to this general matrix. Even vectors then can be, the whole idea of vector operations can be represented by matrices. You do not have to necessarily represent matrices with I, J, and K. And the operations on the vectors that we're going to have in Hilbert space are going to be square matrices. So get used to being able to see how to set up square matrices and how to represent them, and the algebra that goes with square matrices. That's what is being talked about here. Okay. So this is a notation then that we will have for any matrix that we talk about. The elements are numbers, and they are T sub 1, 1, T sub 1, 2, etc., T sub n. So there'll be square matrices. These are entries. So matrix then has an order arrangement, an order set of entries. Okay. And then all the other rules that comes with algebra, then the notion of symmetry, the Hermitian adjoint, on and on, inverse matrices. So all those are there. The inverse matrix is there as well. And so I will give you some problems at some point. That's all I wanted to say on this short presentation, okay? Have a good day, guys.